Now consider photochemistry. Photochemistry, how we have to read, that is photochemistry that should be related to molecular orbitals of molecule. That should be connect pericycle reaction. Okay. So there should be some overlapping region is there, which that should be connect both of chapter photochemistry and pericycle reaction. When we study pericycle reaction, we consider many photochemical concepts, and when we consider photochemistry, we may use many pericyclic reactions concept. Okay, there should be some overlapping things are there. So there should be, we consider, that is first one, molecular orbitals formation. Okay, and they are each homolumo, and how their orbitals are there, and how we consider, that is homolumo gap, how that should be decreased. Okay, so first we consider the phenomena of MO, molecular orbital. Okay, preliminary idea. That is, suppose hydrogen that should be produced sigma bonding. Okay, this is called overlap integral. Okay, this region is termed as overlap integral. Okay, okay, and they all two hydrogen donate one electron each. By mutual sharing, they produce H2 molecule. Okay, okay, this we know. Now both of hydrogen give atomic orbitals, and they produce, that is, two molecular orbitals. Always remember, there should be some rule, that is number of involved atomic orbitals equal to produced molecular orbitals. Okay, so number of involved atomic orbitals equal to produced molecular orbitals. Suppose there should be atomic orbital this. Okay, so that is must be 1 MO, that should be produced 2 MO. Okay, as there should be two hydrogen atom and both of them provide two atomic orbitals, so there should be definitely 2 MOs are produced. Okay, but we have seen 1 MO going to be decrease in energy, so they are more stable. They are termed as bonding MO, BMO, or bonding MO. Okay, other MO get increase in energy, and that should be comparatively more unstable, and they are termed as ABMO, that is anti-bonding molecular orbital. Anti-bonding molecular orbital. Suppose we need H2. They are all hydrogen provide 1 electron, so the 2 electron go on bonding MO. Okay. 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 Now we consider H2 plus. There should be 1 electron. For H2, there should be 1 electron, there should be 1 electron. Okay. So this electron that should be go on bonding molecular orbital first. Okay. Why? Because always system or electron always give tendency to go on lower energy state and more stable state. As we know, for bonding molecular orbital and anti-bonding molecular orbital, bonding molecular orbital having lower energy, so that should be more stable. So electron go bonding molecular orbital to get their stability. Okay. Now if we give, suppose they are supposed, okay, H2 minus, that should be H2 minus. So on that case, one hydrogen give 1 electron and other hydrogen give 2 electron. So suppose one electron give 1 electron and other hydrogen atom, that should be give 2 electron. Okay. So there should be 2 electron placed in this bonding molecular orbital and other that should be placed in anti-bonding molecular orbital. Okay. But now always remember there should be another term that is called bond order. Bond order. What is bond order? What do you mean by bond order? Bond order equal to half into bonding electrons minus anti-bonding electrons. Means that is half of electrons present in bonding molecular orbital minus of electron present in anti-bonding molecular orbitals. If we consider H2, there should be atomic orbitals AO and that should be BMO and there should be ABMO. Okay. So if there are 1 electron each for 2 hydrogen atom, so we get 2 electron in bonding molecular orbital. So the bond order equal to half into bonding molecular orbitals, that is 2 minus 0. We get 1. Okay. Okay. Now consider for H2 minus, suppose there should be anti-bonding molecular orbital. Sorry. So bonding having 2 electron and antibonding having 1 electron. On that case, bond order equal to half into 2 minus 1. That should be get 1 by 2, that is 0.5. So overall, when antibonding electron when electron goes to antibonding, on that case bond order decreases. Okay. That is when electron goes to the antibonding molecular orbital, on that case that is bond order decreases. Now always remember, when electron field, there should be 1 electron field first and then other electron. Okay. That is one go, then this field, then again go this, by maintaining Hund's rule. Okay, by maintaining Hund's rule. If there is 2 degenerate level is there, so electron goes first here, then there, then again there. Okay. 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 Now another concept is bond order that should be proportional to bond length, 1 by bond length. Okay, that should be inversely proportional to bond length, directly proportional to bond strength. Okay. So means bond order increases, so bond length decreases and bond strength increases. Okay. So bond order that should be inversely proportional to bond length and that should be directly proportional to bond strength. So you know, when bond strength increases, bond length that should be definitely get shorter. Okay. When bond strength that should be decrease, so bond length that should be longer. Okay. You can use examples, that is C triple bond C is more strong. So bond order definitely that should be more than C double bond C, then C single bond C. Okay. You can correlate, but there must be some other terminology also used, that is pi orbitals. Okay. Okay. You can correlate, that is C triple bond C greater than C double bond C. By this way, that is bond strength and bond length. You can say that is, there should be, this is not C triple bond C, that is partially bond C. Okay, this is the bond strength order. Okay, so bond length also same, inversely proportional to bond strength. When bond strength increases, bond length definitely decreases. Okay, now we consider, suppose 1,3-butadiene. Okay, electron cloud distribution in molecular orbitals. As we know, this having the structure CH2 double bond CH, bond CH double bond CH2. Okay, so there should be 2 pi bonds and there should be 4 p orbitals. So we get 4 electron in each orbitals. Okay, this is the structure. Okay, now there should be these 2 color give 2 faces. Okay, these 2 color give 2 faces. Sometimes you can use, this is the lobe, there should be plus, there should be minus, for giving the variation. That is for say that is plus is one face, minus is another face. Okay, you can use plus and minus. Okay, now we consider that there should be the energy diagram and there should be defined wave function, that is psi 1, psi 2, psi 3, psi 4. As it is first energy level, so that is node is n minus 1, first energy level. So we can say n minus 1, 1 minus 1, that should be get 0 node. Okay, nodes always having value n minus 1. Okay, as this is E2, so that is n, that is 2 minus 1, we get n equal to 1. Okay, so there should be 1 node is present. Okay, other that should be E3, so there should be 3 minus 1, we get node 2. 3 minus 1, node 2. So there also 1 node, there also 1 node. Okay, again that should be E4, we get nodes, that is 4 minus 1, that should be 3. So we get there 3 node. Okay, we can represent this way also. There should be no node, no node. There should be 1 node, there should be 2 node, there should be 3 node. Okay. Okay. So you can derive that should be E1, E2, E3 and E4. So for E1 we get n minus 1 nodes, that should 1 minus 1 0. E2 we get n minus 1, that is 2 minus 1 in equal to 1 node. There should be 2 node, there should be 3 node. Okay, we can use psi 1, psi 2, psi 3 star and psi 4 star. Now we consider this psi 4 and psi 3 star. Star mean anti-bonding. Okay, anti-bonding. These two goes to anti-bonding. Okay, and these two, that should be bonding. That should be bonding. Okay, these two, that should be bonding. Now by you can always know there should be 4 electrons. 4 electrons. So that should be go on bonding region. Bonding. Okay, so this is bonding and this is bonding. Okay, so these 4 electron go this place and this place. Okay. So by this way, we get this MO diagram. Okay. These are the opposite face. This color show two defined faces are there. So what is the summary? There should be summary is, there must be 1,3-butadiene, the symbol is there, and there must be MO cloud distribution is there, 4 p orbitals, and 4 p orbitals each having 4 electron. There should be energy diagram E, and this is psi 1, psi 2, psi 3 star, psi 4 star means antibonding MOs. That is psi 4 and psi 3 star, star mean antibonding. And psi 4 and psi 3 star are corresponding to antibonding molecular orbitals, and psi 2 and psi 1 are corresponding to bonding molecular orbitals. And as we know, electrons always show to tendency to go on bonding molecular orbitals because of that is extra stability and lesser in energy. That's why they always go bonding molecular orbitals. So 4 electron go on that 2 region. Okay. Now always remember, always nodes are n-1. If energy level 1, we get node 0. No node at all in that position. Okay. And here that is energy state, that should be 2. So we get 2 minus 1. 1 node. So there should be 1 node only. Energy when 3, that is n equal to 2. So we get 2 node only. And that is energy 4. That is we get 3 energy, 3 node only. Okay. That should be clear. Okay. So we get here all phase same. Okay. There due to 1 node we get here 2 phase same, and its corresponding opposite phase, opposite 2 phase is there. Okay. There should be 1 phase and its correspondingly opposite phase is here. Now due to 2 node, these 2 same phase and these 2 that should be defined phase. Okay. And last one, there should be 3 nodes are there. So all 4, so there should be these are defined and these are defined. Okay. These and these are same and these are same. Okay. So due to node, number of node, we get that is defined phases orientation. Okay. When nodes are nil, no nodes are present, so all of the same phases are in one direction and other phase that should be other direction. When we get 1 node only, so there we divide in 2 halves, that is in 1 half that is one type of phase, other half that should be having different type of phase. When 2 nodes, there should be 1, that is 2 terminal lobes having same phase and 2 middle are same phase. Okay. And when we consider n equal to 3, all of the orbitals having defined phase, that is consecutive phases are defined. Okay. When n equal to 3. Okay. Now consider why homo-LUMO gap that should be decreasing. When butadiene produced, that should be produced due to 2 ethylene group, 2 CH2 CH2 combination, we get ultimately butadiene. Okay, due to 2 ethylene group combination we get butadiene. So this is p atomic orbital of ethylene and p atomic orbital of ethylene. Okay, that should be produced pi and pi star homo and LUMO. This is the homo of ethylene. Okay, and that should be LUMO of ethylene. Okay, same also there, that is must be homo of ethylene and that should be LUMO of ethylene. Okay, HOMO means highest occupied molecular orbital. LUMO means lowest unoccupied molecular orbital. So HOMO means that is the highest occupied molecular orbital, means the highest molecular orbital that should be having electrons. And after this, no occupied highest molecular orbital are present. This is we consider HOMO. This is the last highest occupied molecular orbital which having electron. Okay. Second one, LUMO. LUMO is lowest unoccupied molecular orbital. That should be the lowest molecular orbital which will be unoccupied. That should be termed as LUMO. That is lowest molecular orbital having no electron. That should be termed as LUMO. Okay. Now we consider their combination, we produce butadiene. Okay. So we get Psi1. This is only a molecular orbital. This is not HOMO. Psi2 is a HOMO because this is highest occupied molecular orbital, because this is the highest molecular orbital which having electron. This Psi2 is the highest molecular orbital which having electron. If we consider 4 electron for butadiene, so there should be 2 electron and there should be 2 electron. After this, no electron occupations are there. Okay. So Psi2 is the highest electron occupied molecular orbital. Okay. Next we consider Psi3 star, Psi4 star. They are corresponding to antibonding molecular orbital. The star top of the sign, that should be give the idea they are antibonding molecular orbital. Okay. Now we consider this Psi3 star will be the LUMO, because this is the lowest unoccupied molecular orbital. This is also unoccupied Psi4 star. This is also unoccupied Psi3 star. Psi3 star and Psi4 star both are unoccupied. But we have to consider lowest unoccupied molecular orbital. Lowest means that is which are the energy low. So lowest unoccupied molecular orbital is Psi3 star. So Psi3 star considered as LUMO for 1,3-butadiene. Okay. Now okay, up to this. Okay. Now we consider it. This is ethylene, this is butadiene, this is ethylene again. So there, this is HOMO, this is LUMO. So the energy gap is this. Okay. This is HOMO, this is LUMO. The energy gap is this for ethylene. Okay. Now we consider for butadiene. There should be, this is HOMO, this is LUMO. This is. So by this picture you are sure about this. That is butadiene having low HOMO-LUMO gap. Okay. And not only by this picture, actually this is to be happen. In reality, HOMO-LUMO gap that should be decreases when conjugation increases. And as we know, conjugation more in 1,3-butadiene than ethylene. So obviously that is HOMO is more energetic, LUMO is less energetic. So due to this HOMO-LUMO gap that should be decreases in butadiene than ethylene. Okay. Okay. When conjugation increases, HOMO that should be increase in energy, LUMO that should be decrease in energy. So in between of their gap is decreases. And that's why due to conjugation, this phenomena can be there. And as we know, butadiene is nothing but, we can say they are the combination of two ethylene molecule. If we put all the atomic orbitals and molecular orbitals of all of them ethylene butadiene, you can dictate by this picture that HOMO-LUMO gap of butadiene that should be decreases due to energy, that should be energy of HOMO, that should be, this is the HOMO of ethylene and this is the HOMO of butadiene. So energy that should be increasing to the HOMO of butadiene. Okay. And this is LUMO of ethylene and this is LUMO of butadiene. So energy that should be decreasing of LUMO of butadiene. So due to increasing of energy of HOMO of butadiene and due to decreasing of energy of LUMO of butadiene, so overall energy gap between HOMO and LUMO that should be decreases. So HOMO-LUMO gap decreases. Okay, this is the phenomena. Now we consider last one. This is, now we consider photochemical point of view. Okay, suppose that is for butadiene. This is the energy diagram, that is psi 1, psi 2, psi 3 star, psi 4 star. Okay, these are the bonding molecular orbital. This there should be no node, there should be one node, there should be two node, there should be three node. Okay, so this is HOMO, this is LUMO. When thermal use, thermally heat are used, that is normal case. So on that case, the 4 electron goes to bonding molecular orbital. These are the bonding molecular orbital, that is psi 1, that is psi 2. So psi 2 is the HOMO on that case. Okay, but when H nu is used, there should be photochemical excitation can be occur. When H nu is used, photochemical excitation occur. So on that case, in here 1 electron go there. Okay, so now this is the highest occupied molecular orbital. Highest occupied molecular orbital does not depend on number of electrons, that is 1 or 2 electrons present, does not depend on it, but depend on the factor that electron should be present. That is, suppose you give your exam and you did it and you have a mentality that is you will sure have a good marks, but if you do not get first prize, you will not be, suppose sometimes that should be occurred, you do your exam well, you expect you get good marks, but you do not expect you will be rank. Okay, so if you rank, you definitely be happy, but if you not rank but you get a good score, you will also be happy, because this is your expectation. So similar matter, when HOMO means that there should be having at least 1 electron, but if HOMO having 2 electron, this is good, but if HOMO is 1 electron, this is also enough for HOMO. Okay, so highest occupied molecular orbital HOMO does not depend on it how many electrons that should be present. It should be depend on the factor that must be there should be at least 1 electron occupied. Otherwise, HOMO will be considered as unoccupied, and then HOMO that should be considered as LUMO, not HOMO. Okay, this is the factor. So 1 electron go in that position, spin that should be unchanged. There suppose spin that should be unchanged, and now psi 3 star termed as HOMO, that is highest occupied molecular orbital, that is occupied highest molecular orbital. There should be 1 electron present, so this is occupied also. Okay, so this is termed as HOMO. And now the lowest unoccupied molecular orbital is this psi 4 star, because psi 3 star is occupied now, so we have to consider unoccupied for LUMO consideration. We have to consider unoccupied molecular orbital for LUMO consideration. So there are only psi 4 star is the unoccupied molecular orbital, and it is the lowest unoccupied molecular orbital now when H nu is introduced. So when H nu introduced, psi 4 star is LUMO, psi 3 star is HOMO. Okay, we can also sometimes this 1 electron occupied HOMO can be considered as SOMO, that is singly occupied molecular orbital. Okay. So the whole of the summary of the lectures is, First one, photochemistry, that should be concerned about molecular approach and many pericyclic reactions. There should be all atoms, they combine by three defined way. One is ionic bonding, other is covalent bonding, and other is coordinate bonding. If there should be transfer of electron is seen in any compound formation, the compound belong to the category of ionic bonding okay. When mutual sharing of electron is seen, they are termed as covalent bonding, okay. When one atom give their electron and other atom taken as it and they mutual share, on that case they are termed as coordinate bonding. On coordinate bonding, we termed as the atom that should be give their electron, they are termed as electron donor. The atom that should be accept it and mutual share, they are termed as electron acceptor. And when this is the phenomena of bonding. Now consider when atoms are combined to each other, when they combine to each other in covalent bonding, they both of them give their electrons, okay. These electrons mutual shared and produce bonding, okay. So if we consider for single bond, that is sigma bonding, most used example, that is hydrogen. Both of hydrogen give atomic orbital and both of hydrogen give electron, and due to two atomic orbitals, two molecular orbitals are produced. There should be a rule, number of atomic orbitals that should be involved to produce molecular orbital are equal to number of produced molecular orbitals, okay. If two atomic orbitals of two hydrogen atom engage to produce molecular orbital, so two molecular orbitals that should be generated. Now experimentally or actually there is seen that is one molecular orbital get decrease in energy and more stabilized, they are termed as bonding molecular orbital. Other molecular orbital that should be get more energy and that is less stability, they are termed as anti-bonding molecular orbital. Now all systems are always tendency to show to be stable configuration, okay. So always they should go in bonding molecular orbital, okay, rather than anti-bonding. After fulfillment of bonding molecular orbital, then electron goes to anti-bonding molecular orbital. And now always remember, for fulfillment of electron there should be Hund's rule are considered, okay. Now consider, if we consider in slide, there should be always remember in the example of 1,3-butadiene, there should be 4 electrons, 4 p orbital, okay. So that is if we use that is energy diagram, there must be, these are shown as wave function, psi 1, psi 2, psi 3 star and psi 4 star. So the first two are bonding molecular orbitals, so 4 electrons goes to the bonding molecular orbitals, and that is psi 2 is the highest occupied molecular orbital because this is having the highest position and having occupied by electrons, okay. So they are termed as HOMO, that is psi 3 star is the psi 2 is the HOMO, and psi 3 star is the LUMO, as it is lowest unoccupied molecular orbital. That should be unoccupied and that should be the lowest in energy, okay. That's why. Now consider, that is due to two combination of two ethylene molecule we get butadiene. So by this way we see that is the homo-LUMO gap of ethylene that should be more than homo-LUMO gap between that is butadiene, because HOMO that should be increased in energy for butadiene and LUMO is decreased in energy for butadiene. So overall energy gap that should be decreases if we compare butadiene with ethylene, okay. So when conjugation increases, homo-LUMO gap that should be decreases. And last one, there should be when thermal cases is there. So this is the normal case, that is psi 2 is HOMO, psi 3 star is the LUMO, okay. But when photochemical that is reactions is there, that is photoexcitation can be there. On that case, one electron from Psi2 goes to Psi star. One electron go Psi2 to Psi star. So Psi star now Psi star is occupied molecular orbital. So Psi star is termed as HOMO for photochemical reactions, and Psi4 star is termed as LUMO when H nu is used. Okay.